Okay, in the last chapter, we are going to be talking about nonparametric statistics. So up till this point, when we have been doing t-tests and ANOVAs, we have been primarily focused on what are called parametric tests. This chapter, as a nice kind of end of our statistical journey together, is what we're going to introduce nonparametric stats. For instance, are there statistical tests that we can use when various kinds of assumptions are violated, or when we're using other kinds of data that don't really fit neatly into a t-test or an ANOVA. So all the statistical tests that we've discussed so far are designed to test hypotheses about specific population parameters. And since all of these, or since these all concern parameters and require assumptions about those parameters, we call them parametric tests. Now, another general characteristic of parametric tests is that they require a numerical score for each individual in the sample. When we did work with independent samples t-tests, right, we had a continuous DV. When we had dependent samples t-tests, we had a continuous DV, or rather an interval ratio DV. With the ANOVAs, right, we had interval ratio DVs. So that is another general characteristic for these parametric tests. But what if we didn't have a numerical score, like an interval or ratio variable? What happens if we violated some basic assumptions? Or what happens if our sample size is just really low? That is where we introduce the idea of non-parametric statistics. So specifically, we as researchers sometimes have experimental situations that do not conform to those parametric test requirements. So in those situations, you wouldn't want to just use parametric tests anyways. It really wouldn't be appropriate statistically for you to still do that. When the assumptions, and we've talked about assumptions so far in numerous tests, when these assumptions are violated, trying to still use a parametric test or a parametric statistic could lead to erroneous interpretations. And so non-parametric tests actually give us an alternative hypothesis testing technique. And there are numerous types of non-parametric tests. Oftentimes, a lot of parametric tests have a non-parametric equivalent. Now, one thing to keep in mind, though, is that in most cases, a parametric test is going to be preferred over a non-parametric test, right? Even though non-parametric tests are a little bit more relaxed in terms of assumptions, in most cases, if you're able to use a parametric test, you should use the parametric test. So the ultimate question is, well, when might we want to use a non-parametric test? Well, one of the key instances when we do use non-parametrics is if we want to analyze data that are nominal or ordinal. So what makes nominal or ordinal data different than interval and ratio data? Well, nominal and ordinal data is categorical. When you refer to 1 or 2 in nominal data, this refers to categories of different people, right? And when a nominal data variable is what we're essentially measuring, t-tests and ANOVAs don't allow us to really do anything with that. We might also want to use non-parametric tests if the original scores that we're looking at violate some of the basic assumptions, such as having very high variance, or perhaps if we have smaller sample sizes. Smaller sample sizes are actually good for non-parametric statistics, right? And so if we don't have that many in our sample, it doesn't mean that we should just give up and say, oh, we can't run a t-test because we just don't have that many people, right? There could be a non-parametric equivalent that would allow for us to do that still. So here's a nice illustration, specifically just comparing parametric stats versus non-parametric stats that I think does a really nice job. So for instance, in parametric statistics, we assume that the raw scores are normally distributed. We don't necessarily just assume, we can test for normality in here. Whereas in non-parametric statistics, this is distribution free. We're not assuming normality. Typically, we want a decent sample size. Usually, we want at least 10 per group in a parametric statistic because, again, an increase in sample size will give us an increase in power. But when our sample sizes are particularly small, this could make it useful to look at a non-parametric test. Interval or ratio data is primarily used with parametric stats, whereas in non-parametric statistics, we can do data analysis on nominal or ordinal data. In parametric stats, we like to test the assumption of homogeneity of variance. We like to make sure that across our different groups, we do not have widely different variances. Whereas in non-parametric statistics, we can still do some stats if this violation has been violated. We can test for interactions in parametric stats, and they are more powerful. We test for independence, and they're less powerful in non-parametrics. Now, one of the things in parametric stats is that the computations can be complicated, which you all have seen throughout the semester. They're not terribly complicated, but they are a little bit, time intensive here and there. Whereas non-parametric tests are oftentimes less complicated. Now, nominal and ordinal scale data, again, this is what makes them very distinct from interval and ratio. They do not meaningfully convey distance in which scores deviate from some central measure, right? Like the mean. And so here we have to use non-parametrics. These types of tests test the hypotheses with data with any kind of distribution. We can analyze nominal ordinal data, again, this being more categorical. And we are not making inferences about parameters in the population. Now, the most commonly used type of non-parametric test is the chi-square test. And the chi-square test is used with nominal or categorical data, okay? And remember, a nominal variable or categorical data is something like major, something like year in school, right? Your Hogwarts house, right? If you're a Harry Potter fan, right? So something that allows you to be categorized into a specific group, but there isn't really anything beyond that. So chi-square tests compare what we say is our expected frequency. And these expected frequencies are predicted by our null hypothesis. And we compare these expected frequencies with what we actually obtain, frequency-wise, in each of our particular categories. Ultimately, what we're doing is we're comparing what we expect to see and what we actually see. So for instance, if we expected an even split between males and females, right, and we expected to see 50 and 50, and what we actually measured was 25 and 75, these expected values are what we typically talk about in our null hypothesis, saying that, oh, there really isn't any kind of difference. We would expect to see similar levels across each of our categories. But then what we actually observe, we can start to then compare. Does what we observe seem different than what we would have expected? And we can obviously do some calculations to give us a little bit more formal of a conclusion here. So there are two types of chi-square tests. The first is the goodness of fit test. And the goodness of fit test is used when we have one nominal variable that has two or more categories. And what we're testing is whether the observed frequencies of that category, again, the observed frequencies are what we actually count and what we actually measure. And we're testing whether those observed frequencies reflect the expected population frequencies. If we expected an even split, did we actually count an even split? Or did we get a kind of lopsided distribution of people amongst these different categories? So that's the goodness of fit test with one nominal variable with at least two levels. The chi-square test for independence, on the other hand, is used to describe the relationship between two nominal variables. So we're still sticking with nominal data, but the chi-square test for independence is going to allow us to see whether there is a relationship between the counts within these two nominal variables. Now, each of these variables, each of these nominal variables must have two or more categories. So for instance, male and female, and let's say psychology versus no psychology, right? And we make certain counts of people that fall within these categories. If we're only looking at the frequencies and counts, then we are going to be using a chi-square test. With two nominal variables, it's the test for independence. If we're only looking at one nominal variable, that is the goodness of fit. So let's start in this lecture with goodness of fit. Again, with goodness of fit, we have one nominal variable with two or more groups. So our null hypothesis specifies the proportion of the population that should be in each category. What we're ultimately saying in a null hypothesis is that there is no preference among the different categories. If we have 100 people and there are two categories, the null hypothesis would say that there would be an even split. There's no preference among the different categories. So what our null hypothesis says is that the population is divided equally among the categories of our nominal variable. So the general role or the general goal of the chi-square test for goodness of fit is ultimately to compare the data, what we actually observe and obtain, and compare those counts to what we would expect to see in the null hypothesis if that were true. So the expected frequency for each category is the frequency value that is predicted from the proportions in the null hypothesis and based on our sample size. Again, if we are saying that there's an even split between four groups, right? So group 1, 2, 3, and 4. And we're saying that we don't see any preference amongst people in these groups. If our sample size was 100, we would expect to see 25 in each, right? If our sample size was 200, we would expect to see 50 in each, right? So on and so forth. So yes, the frequency value is that is predicted from the proportions, but also from the sample size. Now, usually to get those expected values, we're going to divide our sample size by the number of groups. And we have seen the letter K be used multiple times in this semester, notably when we're talking about ANOVAs. But we're going to divide our sample size by K, which is just the number of groups we have. This is how I got the 25. This is how I got the 50 in these particular examples. So what do we need to run a goodness of fit test, a chi-square goodness of fit test? Well, we need a nominal variable. We need one nominal variable that has two or more categories. The categories need to be independent, meaning that if you are categorized into one of the two groups, right? If you are a male, you are counted in the male group. You are not also counted in the female group. Now, with the goodness of fit test, we want to see an expected frequency of at least 5. So again, decent in terms of sample size, right? Because parametric tests, if you have a sample size of 5, that's not really powerful. But we want an expected frequency of at least 5 in each of our specific categories or each of our particular cells. And this ties in with independence. We want every member in the data set belonging to just one of the categories. Okay. Now, we are going to be calculating a test statistic. We're going to be obtaining this value based on our work. And the test statistic is called the chi-square test statistic. And what this chi-square test statistic does is it just measures how well the data fit the hypothesis. So the expected frequencies define an ideal hypothetical sample distribution that would be obtained if the proportions were in perfect agreement with those that were specified in the null, right? That's what we would expect to see if there truly was no preference amongst these particular groups. We are going to calculate a chi-square test statistic to determine whether we can reject that null hypothesis. Do we have sufficient evidence to say that there actually is this kind of bias towards one specific group? Is there an unequal distribution across these particular conditions? So our formula for the chi-square goodness of fit test, this is measuring how well our observed data fit our expected hypothesis defined by the null. So the chi-square statistic is the sum. We are summing up, that is sigma. The F sub O just stands for the observed frequencies. F sub E is the expected frequency. And so we're going to be summing up as many components as we have K, or number of groups. So for instance, if I write male and female, and we expect to see 50 in each group, but instead we see 25 and 75. We would take our observed frequency for the first category, 25, subtract from it what we would expect, 50, square that difference, and divide by 50, the expected value. Then we would add, in our second group, 75 minus 50 divided by 50. And we're summing those things up. So to decide whether a particular chi-square value is large or small, we must refer to a chi-square distribution. This distribution is the set of chi-square values for all possible random samples when the null is true. So these distributions are, again, going to be essentially defining, well, what's going on when the null is true? Do we have a chi-square value that falls within this rejection region? And if we do, we can reject our null hypothesis. Now, the chi-square distribution is kind of similar to the ANOVA distribution or the F distribution in that it's positively skewed. The formula for chi-square involves adding up squared values. So we are never going to get a negative value. All chi-square values are 0 if everything's exactly equal to the null hypothesis or larger. Now, when the null is true, we expect that our data, what we're obtaining and what we're counting, we would expect it to be very close to those expected values. When the null is true, we expect to get small chi-square values. So our typical chi-square distribution is positively skewed. Now, for the goodness of fit test, the degrees of freedom that we will use to find our critical value, which is, again, is going to serve as that cutoff, is defined as K minus 1. K is just the number of levels or categories, K minus 1. So here's our chi-square distribution. These are our chi-square values when the null hypothesis is true. Just like we've seen so far in this semester in doing different parametric tests, we can define our alpha values as such. And how we define those alpha values is going to determine what our critical value will be. So this is an example of the chi-square distribution table that you'll see on Canvas. And so here we have our degrees of freedom on the left-hand side. And then we have the shaded region that's equal to our specific alpha. So if our alpha is 0.05, we're going to be consulting this particular column here. If our alpha is 0.01, we're going to be consulting this column here, so on and so forth. And so where this column and the row for our degrees of freedom intersect is going to be what we're going to use as our critical value. That, again, we would then compare what we actually calculate in terms of our chi-square statistic to. So what are the steps in solving for a chi-square goodness of fit test? Well, the first thing we need to do is obtain our data. So we need to count the frequency of responses in every category. So what do we actually count? Those are our observed values. Those are our observed frequencies. Then we need to determine, well, what is the expected frequency based on our null hypothesis? Typically, we expect there to be an equal division between the groups. We don't anticipate seeing that one group is preferred over the other. So again, as a reminder, typically our expected value is going to be our total sample size divided by K, the number of groups. In computing chi-square, we compare the observed and the expected values, and we want to determine whether the difference between the observed and the expected values is greater than what we would expect by chance alone. So we square these differences mainly to take into account the fact that some are going to be higher and lower than what would be expected. And ultimately, we don't want these items canceling each other out. We want each of them to contribute specifically to the test statistic. Now, what sets chi-square apart from other tests that we've seen so far is that there are no follow-ups. So remember when we were talked about ANOVAs, and we said, oh, we have 3 or more categories in a one-way between subjects ANOVA. Well, if we have a significant F, we follow that up with post hocs to determine where the significant difference is. Well, in a goodness of fit test, even if we may have 3, 4, or 5 different groups, a significant chi-square is kind of where we end. There are no post hoc tests that we run. We just simply interpret the findings as categories are different from expected or they're not. And then we can kind of put some elaboration on that. We can say it seems that one group was preferred. We can comment on that. We can provide maybe some percentages, but we don't have a post hoc test specifically as a follow-up to a significant chi-square. Now, the chi-square goodness of fit test is not interpreted in terms of differences between categories. If we have a significant chi-square, which means that we have found a chi-square value that is in this region of rejection, if our test is significant, we mostly speculate as to which of the observed frequencies and categories were indeed different from the expected ones. So the chi-square goodness of fit test is one of the few hypothesis tests used that can actually confirm that a null is correct. We can use the goodness of fit test to confirm that what we say in the null, that there is no unequal distribution, we can use that to essentially say that that's correct. So this is an example from a paper that I published in 2018, 2019 for my dissertation. And this is just to show you how I've used chi-square in my research. So what I did was I bred different mice. So I had the J20 mice that had human APP, and then I bred them with the RTG4510 mice that had tau mutations and then a promoter system. And so when you pair these mice together, you get offspring. Now the offspring can have different genetics. So 1, 2, 3, 4, 5, 6, 7, and 8. There are 8 total options that can occur. So offspring from these pairs can have essentially 1 out of 8 chance of being one specific genotype. So the expected frequency of each genotype in this cross was 1 out of 8. There were no significant differences between expected and obtained frequencies in the breeding of this new mouse. Chi-square, this 7 represents our degrees of freedom. That's 8. So 8 minus 1. And then I have the total sample size of mice that I used in my experiment. And then I report my chi-square statistic with my p-value being very, very, very not close to 0.05. And so this is just kind of an applied example of how the goodness of fit test has been used in my own research. Now let's go through a full kind of example to see how we would use a goodness of fit test. And then we'll also talk about how to do this in Jamovi. So a developmental psychologist would like to determine whether infants display any color preferences. A stimulus consisting of 4 color patches, red, green, blue, yellow, is projected onto the ceiling above a crib. Infants are placed in the crib, one at a time, and the psychologist records how much time each infant spends looking at each of the 4 colors. The color that receives the most attention during that 100-second period is identified as the preferred color for that infant. Meaning that if an infant looked at red more than all the other colors during a 100-second test period, they would belong in the red group. So the preferred colors for the sample of 80 infants, that's our N, are shown in this table. We have red, green, blue, and yellow. 25 infants were in red, 18 in green, 23 in blue, and 14 in yellow. Now, our first question is, do the data indicate any significant preferences among the 4 colors? Test at a 0.05 level of significance. And then the second question is to write a sentence demonstrating how the outcome of the test would appear in a research report. So the first thing we need to do is state our hypotheses. So here we have our null hypothesis, which is again just stating that there is no preference among the groups. So in the general population, there is no preference for any particular color. And we can say that all 4 colors are selected equally. And so our expected values are going to be based on this null hypothesis. So if we have 80 infants, right, we would expect 25% of 80 to fall in red, 25% of 80 to fall in green, 25% of 80 to fall in blue, and 25% of 80 to fall in yellow. So 80 divided by 4 gives you 20. So you would expect to see 20 in every particular category. The alternative is that in the general population, 1 or more of the colors is preferred, meaning that there is a preference. Not all colors are selected equally. So there's a few different ways that we can say it. So here we're setting our decision criterion. We have our alpha value of 0.05. Our degrees of freedom, we had 4 groups, 1, 2, 3, 4. So K is 4. 4 minus 1 is 3. And so if we go back to that table, the chi-square distribution table, and we look at 0.05 with a degree of freedom of 3. So degree of freedom of 3 at 0.05 is 7.815, which is where this value is coming from here. That defines our rejection region, meaning that if we find a chi-square value greater than 7.815, then we can reject our null hypothesis and say that there is indeed a preference amongst the particular categories. So the values that we actually counted, right, these are our observed values. So the observed values here are 25 red, 18 green, 23 blue, 14 yellow. So what we can do with this information is now use it to calculate our chi-square statistic. So remember, f sub 0 is just the observed value. F sub e is just the expected value. And we're going to do it for each of our specific groups. So 25 was the observed. So 25 minus 20 squared over 20 plus 18 minus 20 squared over 20 plus 23 minus 20 squared over 20 plus 14 minus 20 squared over 20. This gives us a total value of 3.7 when we add these up. And remember, we're adding them up because we have this sigma notation right outside of this. And anything that follows that sigma notation is what we're adding up together. Now, we calculated a chi-square value of 3.7. Well, what was our critical value? Well, our critical value was 7.815. So because our value was less than 7.815, we fail to reject the null. We fail to reject the null. And the way that you would see this written is we have insufficient evidence to conclude that there is a preference in color. And so we can write comma, chi-square as the statistic, 3. This 3 is the degrees of freedom. N is 80. That's just the sample size, equals 3.7, comma, p less or p greater than 0.05. So our value of 3.7 falls within this fail to reject region. So how do we go about getting this in Jamovi? Well, in Jamovi, how we're going to organize our data is we're going to use 2 columns. The first column is going to be our categorical variable. So this is going to be our nominal variable, and we're going to assign the levels to this variable. So red, green, blue, and yellow. The second is going to be just a column of counts. So what were the observed frequencies for each of these specific groups? So red was 25, green was 18, blue was 23, yellow was 14. And again, that matches what we see here. Now, once your Jamovi spreadsheet looks like this, we have our color in the case of our nominal variable groups, and then we have our counts. We're going to select the box called frequencies. When we select frequencies, we're going to see one sample proportion tests in outcomes, meaning a certain number of outcomes, and you see this called the chi-square goodness of fit. We're going to go ahead and select that box. And when we do that, we're going to be able to move our variables into different boxes. So we're going to move our nominal variable or a categorical variable into the variable box. Notice here on the right-hand side, this specific box is only going to be for nominal or categorical data, meaning, or nominal or ordinal data, meaning categorical. The counts box is going to be where you move that variable counts, as the name implies. Now, this is the simplest way to do the goodness of fit test in Jamovi. If you don't do counts, you would have to list out all of the colors in that first column by as many times as they occur in the actual data set, which nobody really has time to do that. So when we do this, we get the proportions in the color. We see the count, 25, 18, 23, and 14. These counts are thanks to the fact that we have a variable called counts. The levels are coming from the color variable, and then the proportion is just showing how this is broken down. Your results box is found right underneath here. So we have the chi-square goodness of fit test. We have our test statistic, 3.7, our degrees of freedom of 3, and our p-value being 0.296. Now, when you compare that p-value to 0.05, is it greater or less than? And it's greater. So we say p is greater than 0.05. There's insufficient evidence to conclude that there is a preference between the two, or between the groups in this case.